Welcome back again. So in this lecture, we're going to, which I sort of have planned to be not that long a lecture. We'll see how that goes. But we're going to talk about some additional properties of distribution, some of them elementary, some of them less so. And the idea is going to be to set ourselves up in the lecture next to this, where we can apply all of the machinery to talk about differential equations and distributions. Okay. All right. So, so today it's some properties, and we already talked last time about properties of distributions. So this is kind of carrying on in that light. All right. Okay, so so I was kind of do this in list format. So last time we talked about the derivative of a distribution, and remember the definition was that the derivative of a distribution theta, which we denoted by theta superscript 1 like this, was defined by what it did to the derivative of a test signal. Okay, and so the fact is immediately, if you just and there was no restrictions on theta when you do this. So in particular, you can repeat the construction for the derivative of theta itself, and just inductively. In a trivial way, you get that the kth derivative of a distribution is defined by a formula like this. Okay, so derivatives can be differentiated arbitrarily many times. Okay. Which is nice, and certainly not a property that normal signals have. Okay, and moreover, there's, you know, when you have a sequence of differentiable signals that, say, converges in some way, you know, uniformly is normally what you require. Then you want to talk about swapping limits and derivatives. Okay, so in you know, the case of normal signals, you need a bunch of hypotheses to be satisfied in order to swap the limit of a sequence, the derivative of a limit, and the limit of the derivatives. Okay. For distributions, you can always do this. Okay, so if you have a sequence theta j converges the sequence in d prime converging to theta. Okay, and convergence here, of course, means in d prime. All right, so we talked about the notion of convergence last time. All right, then the sequence of derivatives, and you know, I'm going to state it for first derivatives, but of course it holds for arbitrary derivatives. It holds for the first derivative. Okay, so swapping limits and derivatives can always be done for distributions, but, you know, keeping in mind that the limit is defined as a limit in d prime. Okay, so so differentiation is has many nice properties, and as I have indicated previously when we had started talking about distributions, this speaks to the fact that it's easy to work with distributions. the hard part then becomes understanding what you've done in terms of the actual problem that you're working with at that time. Okay. Okay, so these are going to be randomly ordered and therefore quite a little bit disconnected. So we talked about convergence of distributions last time. Okay, we gave the definition. And I just want to say something about convergence like that. Okay. So the mode of convergence in D prime can be thought of in two different ways. And here I'm just going to indulge in some name calling. Can be thought of as weak convergence, or as pointwise convergence. All right, so let's talk about the second first. Okay. So indeed, a sequence theta j converges to theta when, and essentially what you do when you talk about convergence in D prime is you just evaluate each of the terms in the limit and the final result. You evaluate those at a particular argument. Okay, when the sequences theta, so I'm just really rewriting the definition of convergence in D prime, but I want to think about it differently. Okay, and this is, after all, the very definition of pointwise convergence, right? So a sequence of functions converges pointwise when you evaluate those functions at an arbitrary point in the domain, and the domain here is D. That sequence of evaluated objects. In this case, the evaluations take values in the scalar field F, but it may be in some other space. When those sequence of evaluated objects converge to the evaluated object, okay, and you require that hold for each fixed value of the argument. In this case, a test function. Okay. And so the point is, this is the very definition of pointwise convergence. Okay. Okay, now what about weak convergence? Okay. Well, weak convergence is really pointwise convergence in a special setting. All right. So, so the special setting is that of vector spaces and duals. Okay. So this sequence theta j is in the topological dual of the space of test functions. Okay, all right. And so what we're doing is we're defining a mode of convergence in the topological dual. And we're doing that by taking elements of the dual and evaluating them at arguments which are in the vector space. I mean, I'm just repeating what I already said for pointwise convergence, but the thing that's special here is that we're working with a vector space and its dual, and that mode of pointwise convergence in the case of vector spaces and duals is called a weak convergence. So, or sometimes weak star convergence, because we're working in the dual, and the star is meant to denote dual. Okay. All right. So in the case of vector spaces and duals, this pointwise convergence is known as weak, and maybe you want to call it weak star. Okay. Okay. And the fact of the matter is, let me just say a few things about what's going on here in a slightly more general setting. The fact is, you have this vector space which has a topology defined by its convergent sequences. Okay, then you have its dual, which consists of continuous linear mappings. All right. And then what we've done is we've put a topology on here, and we've done that by this device. Okay, by pointwise convergence. Now there's all kinds of other topologies that you can put on D prime. Okay, and this is just an example of one. And so I mentioned that you need to do some work to show that this kind of convergence that I'm talking about here for distributions, this pointwise convergence, that this is actually characterized by the convergence of sequences. Okay. In other words, sequences are enough to characterize this, what's called the weak star topology on D prime. Okay. All right, so that's sort of a general framework for how to think about convergence of distributions. Okay. All right, so functions can be multiplied easily by doing multiplication pointwise. Okay, it's worth noting though that function spaces are not always preserved by that kind of multiplication. So, for example, L2 is not preserved by multiplication. So if you take two functions in L2 and you multiply them together, you don't generally get something in L2. For example, continuous functions are preserved by multiplication. If you take two functions that are continuous and you multiply them together, you get a continuous function. Okay, so although you can always define pointwise multiplication, it's not always true that your spaces are invariant by that pointwise multiplication operation. One way of saying that is to say that it's not always the case that the function spaces that you talk about, and some of the ones that we talk about in this course, namely the Lebesgue spaces, those are not necessarily rings. So they have an addition, obviously, They're vector spaces, and they have scalar multiplication, but you can't necessarily multiply elements of the function space with other elements of the function space and still remain in your function space, okay? And so distributions have none of those properties. And what I mean by that is because distributions are not functions, the definition of multiplication by pointwise multiplication makes no sense, okay? So one cannot generally multiply distributions. Okay. However, there are some kinds of multiplication that make sense. Okay. And the way to think about getting at this is to think about not the distributions, but the test signals, okay, the things in D. And one way to think about that is if you, so D is actually a collection of functions, infinitely differentiable functions with compact support. What kinds of functions can you multiply something in D by and get back to something in D? However, and the answer is, so if phi is in D, and if let's say F is in C infinity, okay, so it's in just an arbitrary, infinitely differentiable function, not necessarily with compact support, okay? It's certainly true then that if I take these as functions and do the standard pointwise multiplication, that, you know, f phi at x is f of x times phi of x, then this thing is in D again. Okay, that's clear, just because the support will certainly be compact because the support of this will be contained in the support of that, okay? And also the product of infinitely differentiable functions is infinitely differentiable, okay? So thus, if theta is a distribution, then theta of f phi makes sense. Okay, and we define a new distribution, and we're going to call that distribution f theta, okay? And this is going to be the product of the distribution theta with the function f, okay? And this function is not just any old function, it's an infinitely differentiable function, all right? Okay, so we define f theta in D prime by f theta acting on phi is theta acting on f phi, of course. Okay, so you have to verify continuity. Okay, so certainly f theta as a mapping from D to f is linear. Okay, and that's really just because this is linear in phi, right? F of phi 1, f times phi1 plus phi2 is f phi1 plus f phi2 and so on. Okay, and one has to verify continuity. Okay, so what you need to do to verify continuity, remember, is that you have to take a sequence of test signals that converges to 0, and you have to show that this sequence of numbers then converges to 0. Okay, and I'm not going to go through it. It's what it boils down to. One can prove this by using the higher order Leibniz formula for product rule. F, G, the kth derivative of two functions f and g, which are k times continuously differentiable, is the sum j equals 0 to k, k factorial over j factorial, k minus j factorial, f j g, oops, g of k minus j. Okay, so there's a formula for the kth derivative of a product, okay, which you can prove just by induction. Okay, and you can see how you might use this. If you take g to be phi, then what you see is that in this formula for the derivative of f phi, you get the derivatives of phi, and I know that those converge uniformly to 0, and they're multiplied by the f's, and the f's on any compact interval, like the support of phi, f and all of its derivatives are going to be bounded. Okay, because f is infinitely differentiable, and so you're going to get something bounded times something that goes to 0, and so that'll go to 0. Okay, and so we're talking about distributions D. There's other classes of distributions, and we'll talk about some of those when we talk about Fourier transforms for distributions quite a while in the future. And this identification of things that you can multiply a distribution by is an important subject. And these are called multipliers. So if you have a class of kinds of distributions, and we don't know what that means yet because we only know one kind of distribution, that's things in D prime, but there's other kinds of distributions. And then given a kind of distribution, identifying what the multipliers are becomes an important thing to do. Okay. All right. Okay, so carrying on, just chatting. Integration. Okay, so we can differentiate, we can also integrate. If theta is a distribution, okay, then it has a derivative, an integral, okay, and the integral we denote by theta minus 1. Okay, if the derivative is theta superscript parentheses 1, then the integral is going to be theta superscript parentheses minus 1. Okay, then there exists theta minus 1 satisfying. Okay, so it satisfies the formula that you expect it to satisfy, namely that when you differentiate the integral, you get the thing back again. Okay, so theta minus 1, 1 is theta. Okay, so funny looking formula, but it's true. All right, now when you integrate functions like you do in calculus, you know that the integrals aren't unique and there's a constant of integration. Well, a similar thing happens here. Moreover, so let me say this. So we call theta minus 1 a primitive of theta, okay? And moreover, this is similar terminology to what you use in calculus, and in calculus, two primitives differ by a constant, and you get a similar statement here. So moreover, if theta minus 1 and let's say theta tilde minus 1 are primitives of theta, then theta tilde minus 1 minus, so they differ. They are the distribution corresponding to a function f, and that f is a constant function. Okay, so a constant function certainly is locally integrable, and so by what we talked about last time, that makes sense. Okay, all right. I don't know what to call this, so I'm going to call it this. All right, so there's all kinds of simple operations that you can do on distributions, that you can do on normal signals that make sense for distributions. Okay, so let me outline some of those. Okay, so first of all, if f is any function on R, I don't even care if it's measurable, the definition still makes sense. And if, let's say, A is some constant in R, then we define shifts and transpositions of f by, okay, so the idea of a shift is that you shift the value of the function, okay? And so the symbols we're going to use to denote shift and transposition are tau a. So we're going to shift by a, and we're going to take f and we're going to shift it by a. All right, and the symbol we're going to use for that is this. Okay, so this is f of evaluated at t is f of t minus a. Okay, and so you can do this for any a and r. Right, and then you have sigma is going to be transposition, and again I'm going to use the same symbol star here, and this is going to be f of minus t. Okay, so this takes the graph of f, and so I'm going to attempt to draw this. Okay, so if this is f, okay, and let's say f looks something like that, then the shift tau a star f is going to look something like that, and this point here gets translated to this point here, okay, and the distance here is a. All right, so that's what a shift looks like. A shift shifts, if a is positive, it shifts it to the right. Okay, if you think about how that argument works, it's a shift to the right for positive a. Okay, and then transposition, it's another kind of fairly obvious, say that f looks like this. And then, oh, sorry, the other way around. Okay, the transposition will look like that. Okay, so you can do this with signals. Okay, so this can also be done with distributions, and the way you do it is by applying the construction to the test signal. Okay. Okay, and the way you do that is you have to take care of the fact that the distribution takes the test signal as an argument, okay? And so you have to think a little bit about how you want the construction to work. And it turns out that the right thing to do is to define tau a star, tau a star theta, okay, by theta applied to tau minus a star phi. Okay, and the reason you want the minus here is because you want it to be the case that when theta is theta f for some locally integrable f, you want the shift here to agree with the shift on functions or signals the way I defined it above. All right, and in order to make that work out, you need to put a minus a there. Okay, and then sigma star theta of phi is equal to theta of sigma star phi. So you don't have to mess around so much with transposition. Okay, and so the point is you can do all kinds of things like this, right? By doing things, by doing things to the test signals, you can infer the same kind of operation on distributions themselves. Okay. All right. Okay, so the last thing I'll talk about is something that's less elementary. Okay, and I'll call this what is a distribution? Okay, so in other words, what I mean is I want to come up with a possible, oh, so I apologize. I knew there was something I was missing. There is. Before I do this, I need to talk about what's called the support of a distribution. So support. Okay, so we have certainly the notion of the support of a function. Okay, so we want to talk about the support of a distribution. Okay, so let's first let O in R be open. Okay, and let's denote by D O F to be the F's in D R F such that the support of F is contained in O. Okay. All right. And so notice that this means that the support of F is closed, right? And so the support of F will never equal O, okay? Because it has to be closed and O is open, right? And so the point is that if you have an open set like this, the support has to be inside the open set and not include the boundary points. Okay. All right, so we say that theta, a distribution, vanishes on an open set O if theta of phi is equal to 0 for all phis whose support is contained in O. Okay, like so. Okay, so apologies for my O's looking like zeros, but I need O. Okay, and then the support of a distribution theta is support of theta is equal to the complement of the union of all open sets O so that theta vanishes on O. Okay, so this union will be open. Unions of opens are open, and so the complement is going to be closed. So the support of theta is always closed. And the idea is that if you have a support, a point in the support, say T, then there's going to be some test signal phi that doesn't vanish at T, and when you evaluate theta on that thing, you'll get something non-zero. Okay, so that's the support of a distribution. And so, for example, the support of delta, the Dirac delta that we talked about last time, is 0. Okay. And so this is a thing about distributions, is that you can have a distribution which has kind of substance to it, like delta, with a point support. Okay, and so moreover, if we have a distribution which is supported at some point 0, and you could shift the support by just shifting distributions like we talked about before. So it's enough to talk about the support being just the point 0. Then theta is a finite sum of Diracs and their derivatives. Sum 0 to k, right? All right, so anything which has a point support is necessarily a linear combination of these Dirac distributions and their derivatives. Okay. And so there's some notation attached to this. So we're going to write d plus prime of r f to be those distributions theta in d r f, so that the inf of the support of theta is greater than minus infinity. Okay, so the support is going to be some finite number. Okay, the support on the left is going to be some finite number. Okay, so so these are distributions which vanish at minus infinity, kind of. Okay. All right. And similarly, d minus prime of r f is going to be theta in d r f. So the soup, sorry, soup of the support of theta is less than infinity. Okay, so these ones will vanish on test signals, which are only 0 for sufficiently large values of t. Okay, so you can imagine doing, I've done sort of 2 arbitrary constructions here that classify distributions by their support. You can imagine doing a host of other things. Okay. Okay, good. So now, now what is a distribution? Okay, and what do I mean by this? Because we know what a distribution is. What I mean by this is they're a way of characterizing distributions, which somehow gives you a lot of insight into how distributions are actually put together. And the answer is there is. Okay. And so here's how this is going to work. All right, so we're going to let okay, so let t in R be a compact subinterval. Okay, now I defined up here dO, where O is open. Now I'm going to define dt, where t is compact. Okay, so denote by dtr. So these are going to be test signals. Satisfying that their support of phi is contained in the interior of t. Okay, so again, so if so the point is that if my distribution t looks like this, okay, so t is a B. Okay, I'm going to consider test signals whose support is contained in the interior. Okay, so the interior is going to be the open interval, and so the supports have to be contained in there. Okay, because the support is going to be closed, and so the support, is compact, because that's what phi, one of the properties of test signals. But it can't be AB. It has to be contained in the interior. Okay. All right, so that's the notation there. All right, and then there's a deep theorem which tells you about what about the structure of distributions, and the theorem reads like this. If theta is a distribution, and if T is compact, then there exists, okay, so there exists a constant M, sorry, I'm thinking of quite the, thinking of the theorem that you use to prove the thing I'm about to state. Okay, so there exists an R, positive in non-negative integer R, such that, and an F in L1 loc such that, okay, theta applied to a test signal phi is equal to theta for this L1 loc takes some derivative of theta applied to phi, okay, and this has to be true for every phi in D of TF. Okay. All right, so what this is telling us is that locally, and by locally I mean for each compact subinterval, okay, locally my distribution theta agrees with the rth derivative of a function. Now the rth derivative here doesn't mean in the sense of distribution of functions. It means in the sense of distribution of distributions, okay, because f certainly doesn't have to be differentiable. Okay, so this will not necessarily be theta of fr, right? So this is the rth derivative in distributions, but nonetheless it tells us somehow the distributions, at least locally, okay, so when you apply them to test signals whose support is contained in the interior of some compact set, it tells us that distributions aren't that complicated, okay, because differentiation seems like a pretty easy thing to do. It kind of comes from some integration by parts formula, so distributions are not that far away from being functions. Is what this result tells us. Okay, so this is not an obvious result to prove, and kind of the most direct way to get at this is that after some initial manipulations, which are already not completely obvious, you can make this boil down to the use of what's called the Hahn-Banach theorem. Okay. And so, these were all the kinds of things that were worked out originally by Schwartz when he developed his theory of distributions. And so we've seen already in our presentation of just signals, we've already seen that this touches upon two major developments in mathematics in the 20th century. namely Lebesgue's theory of integration and Schwarz's theory of distributions. That's one of the things I like about this discipline, is that it touches deeply in significant ways on important topics in mathematics. Okay. All right. So that all aside, what we will do next time is we'll talk about how distributions intertwine with differential equations, because differential equations is really one of the places where distributions see their major use, and that will also be the case in this course as well. Okay, but that's next time.